Welcome back, focused learners, to today's Explainer. Man, I am so incredibly excited you're here because, well, today we are digging into what I can literally only describe as an absolute engineering heist. We are talking about a high-stakes story of pure mathematical resourcefulness in Web3. We're going to see how developers essentially tunneled straight under the rigid physical constraints of the Ethereum virtual machine to pull off something massive.
I want you to keep this visually striking paradox right in the front of your mind as we go. How do you do trigonometry on a blockchain that can't read decimals, right? It sounds physically impossible. There's no way. And this paradox is basically the impenetrable vault of our heist. As we push for the cutting-edge future of decentralized finance, developers were absolutely forced to confront this exact wall.
And to bypass it, they didn't just write a clever new line of code. No, they had to resurrect ancient, division-free integer geometry. In this explainer, we're going to completely unpack how pure, theoretical number theory was used to hack modern blockchain constraints, entirely reimagining how we process math on a network. It's the greatest engineering heist in DeFi.
Okay, let's dive right into Section 1, the EVM math wall.
To really understand this wall, we kind of have to look at the two split personalities of a computer's physical brain. On one side, you've got the floating point unit, or what we'll call the FPU gambler. It handles decimals and continuous math, and it is incredibly fast. But to hit those speeds, chip manufacturers actually burn secret seed tables right into the silicon. The FPU basically throws darts to guess complex math. It's probabilistic and, well, it's lossy. But on the exact opposite side, we have the arithmetic logic unit, the ALU surveyor. It deals strictly in whole numbers. 1 plus 1 is exactly 2 every single time on every single machine. It is strict, it is exact, and it is totally undeniable.
And here is the kicker. Decentralized finance absolutely relies on determinism. It's the absolute law of the blockchain. Thousands of distinct nodes globally literally must compute the exact same state without fail. Because of this, the EVM demands the ALU surveyor's strict logic, and it physically blocks the FPU gambler's floating point math. It fundamentally cannot natively process decimals. So if you ask it to calculate smooth, continuous curves or trig, it either crashes or it burns insane amounts of gas, making your transaction fees just skyrocket.
Which brings us to Section 2, the brute force drill, looking specifically at orb swap.
OrbSwap is this fascinating automated market maker, or AMM, and they propose something totally out of the box, an n-dimensional polar AMM. Basically, instead of trading by moving along these jagged, straight lines, they calculate swaps by rotating around a circle using polar coordinates. In theory, this allows for absolutely massive, hyper-capital-efficient stablecoin pools. But executing these rotations requires calculating complex trigonometric angles. Their official research paper even provides code using standard 64-bit floating-point variables in Rust, F64. But remember that wall we just talked about? Native floats are actively blocked by Arbitrum stylus and the EVM.
So what actually happens when pristine academic math crashes head first into the concrete reality of a smart contract? Well, you get a pretty clunky workaround. To survive on-chain, developers brute force simulated those decimals using heavily hard-coded fixed-point scaling libraries, like PRB math. They used WAD scaling. That literally means multiplying values by 10 to the 18th power, just to mimic a single decimal point on integer-only hardware. Crazy, right?
And this math wall has a very real, concrete impact on your wallet. Basic native integer math on stylus costs about 1 to 2 gas per step. But emulating those floating point calculations using scaled soft float math, that balloons to 80 to 150 gas per step. Simulating a sine wave or a square root using these scaling tricks burns massive amounts of metabolic energy. It is an incredibly heavy computational burden.
Now let's look at Section 3, the wood chipper effect.
Researchers have this super vivid term for what happens when you try to force continuous floating point math into rigid discrete spaces. They call it the wood chipper effect. When non-deterministic hardware, like our FPU gambler, guesses the math and chops off tiny decimal bits to make things fit, the exact identity of the data is permanently mangled. It's literally like putting fruit in a blender, you know? You can never perfectly reverse engineer that smoothie back into the original apples and bananas. The exact mathematical provenance is just permanently destroyed.
And in a high-leverage decentralized exchange, a rounding error isn't just a quirky little math problem, it's a massive financial discrepancy. These microscopic fractions compound.
If you're managing a huge multi-asset stablecoin pool during a period of high volatility, those floating point approximations stretch. This loss of data provenance triggers non-deterministic drift, which leaves the entire AMM system structurally fragile, exposing liquidity pools to severe arbitrage exploits.
Moving on to Section 4, the tunnel. Enter integer recurrence.
Before we unveil the solution, let's just briefly recap the exhausting, heavy baggage of the legacy systems that we are finally leaving behind. We're talking about ditching those massive 10 to the 18 WAD scaling multipliers, the heavy soft float software emulation, the computationally expensive Taylor series, and those convoluted double sequence math methods. Good riddance.
We can directly contrast that bloated execution of OrbSwap's PRB math emulation with a brilliantly elegant discovery from the best state repository, the single-sequence linear integer recurrence. Instead of fighting the computer's native architecture with bloated scaling, this new approach works perfectly with it.
So, the absolute crucial point here is that this method acts exactly like a perfect exact ALU surveyor. A single-sequence linear integer recurrence is a purely deterministic method using only whole numbers. By applying specific sequences, like those found in the online encyclopedia of integer sequences, developers can basically trick the computer into generating flawlessly accurate irrational approximations without ever touching a single decimal point. It tunnels right under the EVM trig wall. Zero floating point guesswork required.
Let's see this in action in Section 5, mastering the 1001 tick.
We really have to talk about ticks for a second. In Uniswap-style AMMs, a tick is a discrete price interval. The absolute standard is the 1.001 tick, which maps to exactly a 1 basis point or 0.01% price change. For stablecoin pools with very low volatility, you want these extremely narrow, fine-grained ticks so you can concentrate liquidity exactly where trades happen and ultimately lower your slippage.
But calculating exponents of 1.001 is computationally exhausting. And this is exactly where the genius of our heist is fully revealed. To create that tick multiplier purely on-chain, without any of that heavy emulation, the best copy square root integers repository uses a brilliantly simple fraction to generate a ratio. Specifically, it uses the integer ratio of 1022 over 1011. This perfectly simple fraction, derived from a single integer sequence, flawlessly approximates the continuous 1.001 price curve. It completely avoids the massive computational overhead and those dangerous rounding errors of OrbSwap's WAD scaling.
Check this out. By just step 2 of the recurrence, that simple 102 over 1020 fraction hits a minuscule error rate of just 0.00485%. It achieves this instantly, dodging all that complex division drifting and the massive overhead of WAD scaling entirely. It relies purely on verified whole number integer logic. It is completely deterministic.
Finally, Section 6, the zero-drift AMM future.
Dropping all that heavy emulation and relying purely on exact ALU integer geometry unlocks an absolute physical energy floor. We are looking at a metabolic cost of just 0.05 picojoules per operation. That is an incredibly tiny fraction of computing energy.
The sheer scale of this shift is just mind-blowing. A standard 16-bit operation, full of complex lossy FPU approximations, burns about 3.70 picojoules. But this pure 1-bit integer ALU method burns just 0.05. That is a jaw-dropping 74 times reduction in metabolic energy. It totally obliterates the gas cost and mathematically immunizes the liquidity pool against those nasty rounding exploits we talked about earlier.
By resurrecting ancient math, we haven't just bypassed the EVM constraints. We've literally opened the door to an entirely new paradigm of highly efficient, zero-drift, quanta-scale financial systems. The tools for flawless execution are now in your hands. So I leave you with this final provocative thought. In an era of zero-drift AMMs, what magnificent, perfectly deterministic reality will you orchestrate next? Thanks so much for joining me for this explainer. Keep learning, and I'll catch you next time.